In the previous video, you were introduced to the properties and behavior of amorphous silicon. In this video, we will explore additional silicon alloys. The learning objectives for this video are to understand the differences between various silicon phases. We will discuss a variety of silicon alloys and how these alloys allow for the deposition of high-performance solar cells. The amorphous phase is not the only silicon phase used in thin-film solar cells. The microcrystalline silicon phase is a hydrogenated silicon alloy with a very complex structure. Microcrystalline silicon, which is also known as nanocrystalline silicon, consists of small grains that have a crystalline lattice and are a few tens of nanometers in size. The grains are embedded in hydrogenated amorphous silicon tissue. Thin film silicon alloys are generally grown on top of a substrate using chemical vapor deposition. We now start growing a film on such a substrate. The yellow areas represent crystalline grains, while the brown areas represent the amorphous tissue. The white fractions in the material are cracks and voids. The crystalline volume fraction of the grown film depends on the condition used for the chemical vapor deposition. We can see on the left-hand side a fully crystalline phase. The material is close to polycrystalline silicon, except that it contains more cracks and pores. These cracks and pores are even more pronounced in the first tens of nanometers of growth, which is known as the incubation layer. The incubation layer is followed by stationary columnar growth, which is usually up to several hundreds of nanometers. We can see that the crystalline volume fraction decreases from left to right and that the material on the right-hand side is fully amorphous. A measure of the crystalline volume fraction is called the crystallinity, which is defined as the volume fraction of the crystalline phase with respect to the total silicon volume. Depending on the deposition conditions, the crystallinity of the nanocrystalline material can range anywhere from fully amorphous to a mixed phase with a few small crystalline grains to a phase which is dominated by large crystalline grains and only a small fraction of amorphous tissue. An example of a nanocrystalline silicon layer with predominantly crystalline grains is shown here. In this image of nanocrystalline silicon on textured crystalline silicon, the small crystals of the incubation layer and the larger crystals of the columnar growth are visible. Research has shown that the best nanocrystalline silicon bulk materials used in solar cells have a network close to the transition region between nanocrystalline and amorphous silicon, with a crystallinity of about 60 to 70%. This second image shows an amorphous silicon and nanocrystalline silicon tandem solar cell. The difference in structure between the homogeneous monocrystalline and amorphous layer and heterogeneous nanocrystalline layer are clearly visible. Let's now look at the various silicon alloys used in thin film solar cells. We've already seen how silicon and hydrogen are used to fabricate hydrogenated amorphous and nanocrystalline silicon. In a similar fashion, other group 4 elements are used in thin film cells. As you may recall, group 4 elements like silicon have 4 valence electrons available to form bonds. An element like germanium can be alloyed with silicon to create a hydrogenated silicon-germanium alloy. Similarly, silicon is alloyed with carbon to create hydrogenated silicon carbide. Another interesting alloy is obtained when oxygen, a group 6 material with 6 valence electrons, is incorporated into the lattice. The resulting hydrogenated nanocrystalline silicon oxide is often used in thin films due to its favorable optical qualities. But why exactly do we alloy silicon with these other elements? The answer is bandgap engineering. By alloying silicon with different elements, we can produce thin film silicon absorber layers with a range of bandgap energies. This is demonstrated in this figure, where the measured optical bandgap energies of a large number of group 4 alloys are plotted as a function of the material density. The colors in this plot indicate different elemental compositions of the group 4 alloys. The visual shows that changes in the bandgap energy of a group 4 alloy can be realized in different ways. We've already seen that the crystalline phase fraction strongly affects the material properties. Additionally, the elemental composition will affect the bandgap energy as indicated by this trend line. Finally, the void fraction or porosity of the material also exerts a strong influence on the bandgap energy of the alloys. Now, why is this range of bandgap energies desirable? Here we see the AM 1.5 spectral power density as emitted by the Sun and observed on the Earth's surface. Amorphous silicon has a bandgap energy ranging from 1.6 to about 1.8 electrovolts, depending on the hydrogen content. So amorphous silicon is able to absorb light in this spectral range. Nanocrystalline silicon has a bandgap energy ranging from that of silicon, of about 1.1 electron volt, to about 1.3 electron volt as it becomes more amorphous and hydrogenated. This means that it already starts absorbing in the infrared part of the spectrum. Amorphous silicon germanium has a bandgap energy ranging from about 1.4 to about 1.6 electron volts, while amorphous silicon carbide has a bandgap energy greater than 1.9 electron volt. Silicon oxide finally has the highest bandgap energy of these alloys of over 2 electron volts. This is to be expected since glass, which is silicon dioxide, has a bandgap energy of about 9 electron volts. The high bandgap energies of silicon oxide and silicon carbide allow it to absorb the highly energetic blue and ultraviolet part of the spectrum with minimal thermalization losses. With this range of silicon alloys, we can design several multi-junction thin-film silicon solar cells. Probably the most studied concept is a micromorph solar cell, illustrated in this figure. A micromorph cell consists of an amorphous and a nanocrystalline silicon junction. Amorphous silicon is placed on top since it has the highest bandgap energy. These thin yellow layers in between are intermediate reflective layers. Let's take a quick look at the Venn diagram of this tandem device. We first have the Venn diagram of the amorphous silicon top cell, followed by the nanocrystalline silicon bottom cell. The blue and green short wavelength light is absorbed in the top cell, while the red and infrared light is absorbed by the bottom cell. Holes generated in the top cell and electrons generated in the bottom cell can be collected on either side of this device. As explained in the preceding section, a tunnel recombination junction is required between the N layer of the top cell and the P layer of the bottom cell, which allows the electrons from the top and the holes from the bottom to recombine. The current record micromorph device was developed by AIST and has a stabilized efficiency of 12.7%. The reason for adding the term stabilized will be explained in the next video. Naturally, cells with more than 2 junctions can also be made to even further increase the spectral utilization of the solar cell. An example of a triple junction solar cell is shown here, with an amorphous silicon junction on top, an amorphous silicon germanium junction in the middle, and a nanocrystalline silicon junction on the bottom. This 16.3 initial efficiency triple junction device was made by the former US company United Solar. The spectral utilization of this device is shown in this figure. The spectral utilization is relatively high, especially in the ultraviolet and visible part of the spectrum. Furthermore, we see that the EQEs of the individual junctions overlap. At 450 nanometer, light is only absorbed by the top cell. Light around 550 nanometer is utilized by the top and middle cells, while light around 650 nanometer is utilized by all 3 junctions. The overlapping EQEs of the junctions are unlike those of, for instance, 3-5 multi-junction cells, where the EQEs of the individual cells are block functions. 3-5 based technologies will be discussed later in this course. Consequently, optimizing thin-film silicon multi-junction solar cells is a complex interplay between the various absorber thicknesses and light management concepts. Now, in summary, we discussed the phase transition between nanocrystalline and amorphous silicon and defined the concept of crystallinity as the volume fraction of the crystalline phase with respect to the total silicon volume. We then looked into the bandgap engineering opportunities provided by alloying silicon with various elements. Finally, we discussed a micromorph solar cell and an example of a triple junction solar cell using silicon alloys. In the next video, we will discuss one of the inherent challenges of amorphous silicon, namely light-induced degradation.